Yes, you can also do derivatives of these things. So let's say we take this one up here and we find the derivative of it. So of course this function can also be written 1 minus x to the negative 1. That way we don't have to do quotient rule on it. We can just do power rule. And we could do a derivative of it. So let's do the derivative of 1 minus x to the negative 1. Well, using chain rule, that's going to be negative 1 minus x to the negative 2. All right, so that's power rule. And then I have chain rule because there's a negative inside parentheses there. So I'm going to have to go times negative 1. So what I end up with for the derivative of this function, 1 over 1 minus x, is positive 1 over 1 minus x squared. Yeah. And so now what I can do to find a series representation for that is just go term by term the derivative of the function that I started with. So I would do the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. And of course the next one's going to be x fourth, so it'll be 4x cubed plus etc. All right, and that has to equal 1 over 1 minus x squared. So now I just have to find a way to describe this. So you can do some from n equals 1 to infinity to describe it. I stuck with n equals 0 to infinity for this one. And then I just saw that what you have here is nx to the n minus 1. So that way you can also see that from the original function, from the original series x to the n, right, the derivative of x to the n is nx to the n minus 1. That's just power rule. And then when I start with n equals 0, I get 0 for my first term. And then n equals 1 gives me 1x to the 0, so that's the 1. And then n equals 2 gives me 2x to the 1, so it gives me all those terms. So that's just doing a first derivative of this function. So we can do that as many times as we want. We can do another derivative. So basically, these are ways to develop new series out of the old ones. And by the way, when you do this, whether you do multiplication like we did here, whether you do a substitution like we did here, the interval stays the same. Although in one of the homework problems, we're going to see how if you do a substitution, you might have to revisit the interval. On these ones, we don't, but we'll look at an example where we have to revisit the interval. When we do integral or derivative, we're still going to just keep the same interval. So let's do another derivative. Let's do the second derivative. Let's do the derivative of this one. So let's do the derivative of, this is 1 minus x to the negative 2. 1 minus x to the negative 2. So I'm going to have, using power rule, negative 2 times 1 minus x to the negative 1. But then I have chain rule. I have negative x as an inside function. It's going to be times negative 1. This actually, when I lower this exponent 1, it should be to the negative third power. To the negative third power. Yeah. So then what I have as the derivative of this guy is 2 over 1 minus x cubed. 2 over 1 minus x cubed. So what's that going to be equal to? Well, let's look at term by term first, and then we'll look at what the series would have to be. So, yeah, I'm just looking at different ways you could do that. The derivative of 1 is 0 again, and then I have plus 2, and then I have 6x, and then I have 12x squared, and then my next one's going to be 20x cubed, and it's going to keep going like that. All right, so there are different ways you could choose to represent this. I chose to do n equals 0 to infinity again. I think your book does 1 to infinity on this one, but you'll see how you can just manipulate the expression over here, and that will change what your index variable is by 1, and you can really just account for it. So what I have here is, like, now we're looking at, this is n equals 1, n equals 2, n equals 3, n equals 4. And this n equals 0 is going to be another 0 term, the way that I set it up. And then what you have here is, like, I took n minus 1 and multiplied it by n, right? N minus 1 and multiplied it by n. So that's sort of the key here is I have n minus 1 times n. And then what's my power of x? My power of x is 2 less than n. So times x to the n minus 2. And I liked doing it this way with the x equals 0 to 1 because you can also see then that if I do the derivative of this function, I would do n minus 1 times the n, just using the power rule, drop the exponent 1 and have n minus 2. But you can change it around. You can do some n equals 1 to infinity of n times n plus 1, x to the n minus 1. Like there's lots of ways you can sort of manipulate this around. The way I've done it, when n equals 0, this term is 0. When n equals 1, this term is 0. So it doesn't actually start giving you non-zero terms until the n equals 2, and then I have 1 times 2 x to the 1, x to the 0, which is what we have there. And then for n equals 3, I'll have 2 times 3, which is 6, x to the 3 minus 2, which is 1, so I get the 6x term. So it's just a matter of finding this formula over here to describe the pattern that you see here. And then what's significant about that is that you can generate new functions that have another series description. So that was doing derivatives. Guess what? We can also do integrals.